Acid-base titrations. So now that we did a titration, you're going to know what we're talking about here. So a titration is just a lab technique. We take a solution of known concentration and we react it with a substance in a solution where we don't know the concentration. The goal is to find that unknown concentration. We add the one solution to the other until the reactants are at their stoichiometric ratio, and that's called the equivalence point. So if the balanced equation has a 1-to-1 molar ratio, we'll have added a 1-to-1 molar ratio of these two reactants. We calculate the unknown concentration using stoichiometry. When you have an acid-base neutralization reaction, there's nothing to see. And so how do you know when you've added the right amount of stuff? You use an indicator. The indicator changes color when the solution undergoes large changes in acidity or alkalinity. At the equivalence point of any acid-base titration, the number of moles of acid, H+, equals the number of moles of hydroxide ion. You're right at that, equal the equivalence point, sometimes called the end point. There's a sample titration. Here is the net ionic equation. Hydrogen ion plus hydroxide ion giving water. So there's hydrogen ion in the flask. It could be from acetic acid or hydrochloric acid or any sort of acid. And then we have hydroxide ions in the burette. Could be sodium hydroxide is typically what we use, but it could be something else. As we add sodium hydroxide ions, add hydroxide ions, they react with the hydrogen ions and they form water. And so there's less acid here. And we keep adding until we have added enough hydroxide ions to react with all the hydrogen ions. Now there is no longer an excess of hydrogen ions. And so the pH changes. The indicator is sensitive to that pH change and gives us a color. Now I think many of you noticed that one drop can send you from pale pink to bright fuchsia with phenolphthalein, right? So it's pretty sensitive, and it works pretty well. This should look familiar. Here's actual pictures. As we're adding the sodium hydroxide, we see a little pink in the center of the liquid in the flask because it hasn't mixed up and reacted yet. And when we get to the end point, it will all be pink. Phenolphthalein. It's just kind of fun to say, and it's more impressive if you can spell it. The pHs and the THs, there's something about that. So here's an example. Stoichiometry, start over. Titration calculations end up being solution stoichiometry calculations. That really is the best way to think about it. You may have learned some other kind of shortcut method. I don't recommend it. It's another thing to remember, and sometimes it steers you wrong. So let's look at this. To standardize an HCl solution, you put 50 milliliters of it in a flask with a few drops of indicator and put 0.1524 molar sodium hydroxide in a burette. The burette reads 0.55 milliliters at the start and 33.87 milliliters at the end point. Find the molarity of the HCl solution. So they're basically telling you a very brief story of what someone did in lab. This is what you measured, and this is what you were doing. So this is a titration, and we need to look at the equation. What's the acid? HCl. And what's the base? Sodium hydroxide. Okay, and these react, remember in an acid-base reaction, the anion and cation are going to switch, they're going to swap partners. So the chloride came with the hydrogen, it's going to leave with the sodium. So we're going to end up with sodium chloride and water. Very important to make sure this equation is balanced. One chlorine, one sodium, one oxygen, 2 hydrogens, and 1 plus 1 is 2 hydrogens. This is a monoprotic acid, and this base has 1 hydroxide per mole. And so this is going to be a 1-to-1 ratio. We can use that equation to help us organize this information. 50 milliliters of what? Of the HCl, right? So 50.00 milliliters of that. The next number, 0.1524 moles per liter sodium hydroxide. So I'm going to write that under sodium hydroxide. 0.1524 moles over liters. Because it's so easy to forget what the capital M means. So just write it out. Now, what are these two volumes going to tell us? How much we added. Did we add 33.87 milliliters? No. We need to subtract, right? So let's do that on the side. We take 33, you see that okay? 33.87 milliliters minus 0.55 milliliters equals 33.32, right? It's always scary when I do math in my head. Oh, and that ended up right under there where it's supposed to be. Find the molarity. So our question is about the HCl, and we want moles per liter. This is stoichiometry. And what's at the center of all stoichiometry maps? Mole to mole. So the one that we have the information about is the sodium hydroxide. So moles of sodium hydroxide. And the one we want information about is the HCl. So that's in the middle. We are given the volume of sodium hydroxide and the concentration. Which one of those would be our starting number? The volume, right? So we're going to have a volume of NaOH, and then using the concentration, we can figure out how many moles of NaOH. The mole ratio 1-to-1 tells us that we can figure out the moles of HCl, and we want to get to moles per liter, molarity. How do we calculate molarity of something? Moles per liter, right? So we need moles of HCl, and we need to divide by the volume, right? So that guy's up there. So let's start. We're going to start with the 33 point, I can't see my own writing, 32 milliliters of NaOH. I'm going to ignore that milli for now. Just, I have an inkling of what's going to happen later because I've actually used this slide before. So I want to go from volume, because milliliters, liters, we can figure that out. We're going to go to moles of sodium hydroxide, and then we're going to go to moles of HCl, and these need to be conversion factors. So I'm going to have, this is moles per liter, right? Oh, I didn't leave any room for the number. Oh well. I'll squeeze it in there somehow. What a mess. 5, 2, 4. You see that? Yes? That's a good question. There are a lot of people that like to use the dilution equation, M1V1 equals M2V2, for titrations. I don't recommend it because it only works if the mole ratio is 1:1. If it's not, like it was with your citric acid titration, you'll end up with a number that's off by a factor of 3. And that's not good. So instead of trying to figure that out and factor it in, I think it's better to just do something we already know, stoichiometry. It's really not any more work. I actually taught out of a lab manual that was using that approach, and they got the equation wrong in the lab manual. I'm like, really? Wow. I just didn't even know what to say about that. But that was a very good question. So we're looking at these and we're recognizing, okay, that's milliliters and that's liters, but we can fix it. So we're not going to let that bother us. This is moles of sodium hydroxide, and so I want moles of sodium hydroxide down here. And those are going to cancel out. And then, now this is where we deviate a little from the pattern of dimensional analysis where we've just been multiplying by unit factors, factors that equal 1. So there's two ways you can do this. If this kind of stuff is confusing for you, then you should probably just stop here. You'll have to deal with these units. Just stop here with the moles of HCl, and then in a separate equation, divide by the volume. And if you want to see that after I do it the other way, I'll be happy to show you. But I'm just going to kind of keep going here. So after I sort out that mess, what I'm going to end up with is moles of HCl. I want the molarity, so I need to divide by the volume. So I'm going to multiply by 1 over the volume. What's the volume of HCl? 50.00 milliliters, right? Well, would those milliliters cancel? Sure. We've got milli and milli. Those are going to cancel, and liters are going to cancel. And now we've got liters in the bottom and moles in the top, units of molarity. This is a situation where you could convert to liters and do the calculation and then convert the other milliliters to liters, but the conversions end up canceling each other out. I left my calculator again. So we've got 33.32 times 0.1524. Oh, I forgot to write numbers in for the mole ratio. In this instance, it's 1:1. And that's why if we forget to take that into account, it doesn't matter this time, but other times it will. How many significant... Yeah, because we've got volume of sodium hydroxide down here. So the sodium hydroxides are okay, and then the milliliters are okay. So how many significant figures should this have? I heard a noise, but I couldn't tell what number the person said. 4, thank you. 0.1016 moles per liter. Does that make sense? Does anybody want to see it the other way? Doing it in 2 steps. Do you? That's fine. Okay, so everybody okay with this one? So what I'm going to do is I'm going to back up a little bit. So we're back at this point, and we're trying to cancel out units, and we see, oh, that's not going to work. We have to account for the milli in there. So we have liters on the bottom. I want to put liters on top. And we have milliliters on top, and I want to put those on the bottom because I want milliliters to cancel. And it's okay that we stuck it way at the end. They still cancel out. And now all our volume units went away. What does milli mean? 10 to the minus 3. I never put 10 to the minus 3 with the milli. I put it on the other side. So 10 to the minus 3. So I've got 33.32 times 0.1524 times 1 EE minus 3. No, that didn't work. I believe it should be 0.005. Is that right? Anybody? Okay, so we shouldn't round it yet. 7,968. I ended up with 5,077 because my calculator misunderstood me. I'm using the app on my iPhone, and it's not the best scientific calculator. Moles of HCl. Now that should have 4 sig figs, so the last significant digit is there. I don't want to round that yet, though, because we're not done, right? That's moles of HCl. We need the concentration in molarity. Molarity equals moles over liters. So that equals that number of moles I just calculated divided by the volume, 50 milliliters, and then I need to convert milliliters to liters. So I'll have milliliters on top and liters on bottom. Milli means 10 to the minus 3, and so the milliliters cancel out. Come on, phone. And I miraculously arrive at the same answer. This is our final answer, so we can round it. Moles per liter. It's the same thing, just broken into 2 steps. So do whichever one makes sense to you. If the first one just doesn't make sense to you, don't do it that way. I wrote these out, the milliliters to liters. Now, some of you have a good grasp of the relationship, and you know you can just move the decimal point over 3 places, and you never get it wrong, and you're good. And you can do that also. Any questions? Stoichiometry problems with titrations are an important part of Chem 1A. And we did this part of 4.8 already.